Yes, so the video, I think the meeting got terminated. Don't know because of what reason. So I think we were discussing this. So we were seeing the two forms of QPSK. Now the difference in the two forms is that, let us say if this is your constellation diagram, then you rotate. If you rotate this constellation diagram by pi by 4, you will land up with this constellation diagram. Okay. So difference is that both the constellations are, you can say, at a pi by 4 phase with each other. Okay, or it means if I rotate one of the constellation by pi by 4, I will end up with the other constellation. Now the reason behind studying this constellation is that in this constellation, modulation of both cosine and sine carriers take place. Okay, take place for each of the points constellation points. But here only one of the carrier is modulated. Okay, so this is like a single BPSK system. Each time whatever you transmit, this is like two BPSK systems operating, you can say, parallelly, and you add both of these output to transmit. So we are not going into depth at which one should be preferred or which should be studied, but it was important to bring is two dimensional. Let me check. Okay, signal constellation is two dimensional with M message points. With M message points. Okay, and they are equally spaced. You must remember this. Equally spaced. On a circle, of radius root of E, and center at the origin. Okay. Now let us see this figure in the textbook, because while drawing it won't look that much nice because we have to draw capital M number of points. Okay. So this is what was, these are the two commonly used constellations for the QPSK which I was discussing. So you can just go and read it yourself, pi by 4 shifted QPSK. Although I don't think that it has been discussed in section B, that's why I am not doing it here. But if at all it has been done there, as this is to the best of my knowledge, then with the background which we have built, you can simply read it. Okay, I have built sufficient background for QPSK, which will allow you to read yourself also several other things, and you can comprehend them well. Okay, comprehend it well. Let us come to MREPSK. This is what is the constellation diagram is. Okay, So you have, let us say, one point here, then another. This is for the 8 PSK or 8 possible points. So this 2 pi radian will be divided into 8 points. So it starts at 0, then it is like pi by 4, then it's pi by 2, and then it is 3 pi by 4, and then this pi, and then this. So you will get 8 points. These dotted lines are nothing but the decision regions. Okay, decision regions, you know. They are the regions which will tell you that if at all point falls in this region, then you will decode it as M2 if this falls in this region. So this region is designed based on ML criteria mostly. Okay, although map criteria would be the optimal criteria, but for that you need prior probabilities. Okay, so it is important to derive the probability of error. So probability of error for MPSK. Okay, so this we are following from Process. Okay, remember that. Okay, so Simon-Hakin doesn't give. Okay, Simon-Hakin gives it from the perspective of union bound. Okay, and since we have not covered union bound because the number of lectures were less, so I have taken a different approach which is presented in Process communication systems. Okay. So for it, let us take a case. Since see one thing, that if I try to obtain the probability of error for this point, okay, then it would be same for all the other points. Reason being, we have the constellation points as equispaced, okay, and the decision regions are also very well symmetric. It means जितना width decision region का इसका होगा उतना ही बाकी सबका होगा. And because of this circular symmetry, you can see that if I obtain the probability of error for this point, the same probability of error will be there for other points as well. Okay, means that if I assume that I have transmitted this, so if I transmit this, I will obtain the probability of error. So that is same as if I transmit this and try finding the probability of error, because they are all linked through to each other by a simple rotation mechanism, and this rotation doesn't affect your probability of error. Now there are several ways to see it. So I would say that you look at the way you would appreciate. Okay, or what the best way is that you derive. Okay, आप derive करिए हर एक point के लिए और आपको बाद में पता चलेगा कि वो same है. तो generally the standard way is to assume that let root of e comma 0. Yes, one more thing, that if at all in MPSK, how many bits will be there in one point? So you will have log to m bits per symbol or per point. Okay, so your symbol time t would be tb into log of 2m. remember that this would be the symbol time, not symbol time would increase. So ये एक बड़ी कमाल बात है कि जैसे जैसे आप मॉड्यूलेशंस बढ़ते जा रहे हैं, बीपीएसके में सिंबल टाइम टीबी था, क्यूपीएसके में 2 टीबी हो गया, फिर एमएरीपीएसके में वो log 2m टीबी हो गया. तो इसका मतलब ये है कि आपका जो टाइम है सिंबल का वो बढ़ता जा रहा है एज यू आर basically increasing the possibility of more bits in a symbol. But what is the impact it has? The biggest impact it has is that if your pulse width is small, the frequency consumption or the first null bandwidth is higher. Okay, so BPSK में frequency consumption या band consumption या base band में जो first null आएगा वो ज़्यादा आगे आएगा as compared to QPSK and as compared to MADPSK, because the symbol time, the timing is increasing. So if you have a greater time coverage, your frequency coverage would be lesser. Okay, because the changes are now that much, are not now that much abrupt. Okay, so this you should appreciate. We will see it when we will discuss the bandwidth efficiency. So let this e comma 0 be the transmitted point. Okay, so we know that if this is the transmitted point, so you will receive what? So you will have root of e plus n, and r of t is n. This is the received point. Now these are the n, small n is nothing but a random variable with 0 mean and variance n naught by 2. So right now I'm writing few things which I have proved basically in our lectures earlier. So I would assume that you will go back and read. So R1 and R2 are jointly Gaussian random variables with expected value of root of E 0 and let us call it to be sigma r square. I mean, this is a common term which to be used for each of the sigmas. Okay. So we now know that what is f of r. We can write their joint density. Joint density is nothing but 1 upon 2 pi sigma r square e raised to power minus of r1 minus root of e whole square plus r2 square divided by twice of sigma r square. Okay. So this is the joint PDF of R1 and R2. So this basically we are following from Prokis, because if at all we go the way Haken does it, then it would be really difficult for us to understand because we have not done union bound. Okay. So without union bound, we can resort to this approach. Okay. Now let us write this in an alternate form. In an alternate form, which will be more suited to our purpose. Our purpose is to find that this R1 and R2 exceeds these boundaries. Okay, so अगर आपका R1, R2 का जो point है वो इसके अंदर कहीं भी है, इस रीजन के अंदर, तब आपकी एरर कमिट नहीं होगी. बट अगर वो किसी और रीजन में चला जाता है, इट मींस इट गोज टू दिस और इट गोज टू दिस और दिस और दिस और दिस और दिस, इट मींस अदर 7 regions, if it goes, you are going to commit a mistake. Okay, so we have to find that. So we represent this in an alternate form which will help us do that. So in an alternate form, let us set or choose whatever you can set v is equal to, this is nothing but the magnitude of that vector, and let us select this as the phase. So this is tan inverse r2 by r1. So what would be your, now we represent the PDF in terms of these two numbers. Okay, this is equal to v upon 2 pi sigma r square e raised to power minus of v square plus e minus twice of root of ev cos theta r divided by twice of sigma r square. Okay, so this is your, so I am not, this is then by transformation of variables. So I will give you a reference that you can read transformation of variables. This you must have done in your, you can see Ross's book. Okay, I think that is the book which is followed here in the course probability statistics. So you can go back and see. I think you have done in that course. So I am not putting up time to explain this. This is very simple. You take the derivative, take the Hessian matrix, you get in Jacobian matrix. I think you will get whatever, I don't remember, and then you have to take the determinant of it. Okay, quite a simple strategy. Now, what is the marginal PDF of theta? Let us obtain. So अब हमने क्या किया? देखो ये पॉइंट था, हो क्या रहा था, ये आपका एक R1, R2, सपोज एक आर्बिट्ररी पॉइंट है. This is R1, R2. So we had the PDF in terms of R1, R2, but now the PDF in terms of these two variables, theta R और V. अब इन दोनों के टर्म्स में हमें PDF आ गया. अब एक चीज आप देख सकते हैं, अगर आपको इसके अंदर एरर निकालनी हो और मैं आपको कोई भी पॉइंट दूं, उस पॉइंट की स्केलिंग से कोई इफेक्ट नहीं आएगा. इसका मतलब ये है कि अगर मैं ये पूछूं आपसे, इफ आई गिव यू R1, R2 and I ask that if I give you a chance to amplify it, amplify means I do this, a R1, a R2. So what I am ultimately doing, I am increasing its magnitude. Will it change your probability of error? No, it won't, because this will not change the orientation. It will only change its length. So it becomes like this. Okay. So maybe in some direction, this in the same direction, this will increase the length, okay, of this vector. So error probability is not dominated by this, it is dominated by this angle. It means if आपका जो ये point R1, R2 है, ये किस region में lie करता है, ये will be dominated by this angle which it has, okay. So theta r से हमें मतलब है, इसके magnitude से हमें मतलब नहीं है. Okay, by what will be the magnitude of this? This will be under root of a square r1 square plus a square r2 square. So this will be, sorry, this should be square, not this. So if I take a as common, so this becomes a times root of r1 square plus r2 square. So I have just increased the magnitude of it. So इसका magnitude क्या था? Root of, so what do we do? So we obtain now the marginal PDF of theta. That is the main point here. Okay. Hence, we obtain the marginal PDF of theta r. So how do you do that? It is quite simple. You just integrate theta r is equal to, you integrate the joint PDF over v. Theta into d theta, dv, sorry. Okay, you just integrate over v. So the answer you get is, this is equal to 1 upon 2 pi e raised to power minus of twice of e by n naught sine square theta r. This is, I think, should be e divided by n naught, otherwise it might seem to you that it is this sine square theta r is in the denominator. E by n naught integration 0 to infinity v into e raised to power minus v minus root of 4 e by n naught cos of theta r square by 2 dv. So in our postgraduate courses, generally we do this derivation. This is very simple, but we do it there. So I am not doing it here because it doesn't matter to us what is the result, because we will see that for our interest, we can obtain the expression without solving this. Let us see. So we can see when root of e comma 0 is transmitted, decision error is made if the noise causes the face to fall outside the range Okay, how? Let us see it. So जो हमारा ये था सर्कल, ये हमारा पॉइंट था, and this is this decision region. You can see it from the figure. So this is what this angle is. This, okay. How come this has come? Okay, so 2 pi by m is the width. Let me just draw it. That will give you idea. Suppose आप जो इसका next point है, suppose this is the next point. So you know that this next point will be at an angle of 2 pi by capital M. So you just draw a line here which is at the angle of pi by M, means exactly half. and similarly you draw a line which is at an angle of minus pi by m. So this becomes the decision region. This is your D1. अगर इससे बाहर जाएगा तो आपकी एरर होगी, दैट इज क्वाइट ऑब्वियस. ओके, दिस डिसीजन रीजन जो कंस्ट्रक्शन आया कि ये हाफ एंगल पे होना चाहिए, ये आपका एमएल लॉजिक से, मैक्सिमम लाइक्लीहुड से, जो हमने डिस्टेंस डिकोडर निकाला था, ये उससे आएगा. ओके, सो वी कैन सिंपली फाइंड अ सिंपल एक्सप्रेशन. सो हेंस probability of symbol error is P of m is equal to 1 minus integral minus pi by m to pi by m f of theta d theta. Okay, so this is your expression for finding the probability of symbol error. Okay, ये तब है जब आपने root of e comma 0 ट्रांसफर किया, but the claim is that this is same for all the points. It means जो आप बाकी सब पॉइंट्स लिखेंगे, बाकी सब पॉइंट्स की भी यही, मतलब जो जो एक्सप्रेशन आएगा सॉल्व करके वही उन सब का भी आएगा. So let us take special cases. Okay, so for m equal to 2, m equal to 2, that is BPSK, and m equal to 4, that is QPSK. Okay, probability of symbol error is known to us. Probability of, remember this is not bit error we are discussing, we are discussing symbol errors when we talk of QPSK and MEPSK. For BPSK this is same as bit error. Okay, so probability of symbol error is known, we have derived them, we know it. So let us check. So if you put m as 2 and m is equal to 4, when you solve this, that is first of all you have to solve this integration, and then you solve this integration, you will get an answer, and that answer will match to the expression which we got. Okay, but what about m greater than 4? Means for a general value of m which is, let us say 8, 16, what will you get? Okay, generally we talk of this so that log 2m is a integer. Okay, so that's why we will take m as some multiple or some power of 2's. Okay, the 2, 4, 8, then 16. Okay, the problem with m greater than 4 is this integral into does not give a closed form result. Now what is the meaning of this? इसका मीनिंग ये है कि जब आप इसको सॉल्व करने पे जाएंगे तो एक एक्सप्रेशन नहीं आएगा, उस एक्सप्रेशन में कोई ना कोई ऑपरेशन पेंडिंग रह जाएगा जो आप एनालिटिकली सॉल्व नहीं कर सकते, आपको न्यूमेरिकली करना पड़ेगा. इसका मतलब है कोई ना कोई इंटीग्रेशन आपका ऐसा रह जाएगा जिसका एक फाइनाइट आंसर नहीं है. मींस यू कैन नॉट एक्सप्रेस इट इन टर्म्स ऑफ सम अदर फंक्शन, दैट यू हैव टू सॉल्व इट. तो दैट इज द मीनिंग कि क्लोज फॉर्म रिजल्ट नहीं आएगा. सो and we have to solve it numerically. Okay, so what do you do? So how do you analyze it? But there is one catch. Okay, but there is one case. But in one case where if we assume here, if we consider large m and e by n naught as much greater than 1, means a very high value of e by n naught for theta less than pi by 2, is verifying significance of large m and m. We can get an approximate closed form expression. I don't think that this is right now required. We will need it for some other thing. ओके सो इस केस में अगर आप m की वैल्यू लार्ज लेते हैं, जैसे 8 ले लेते हैं, 16 ले लेते हैं, वो भी काफी हाई रहेंगी. और अगर आप SNR, द सिंबल SNR को हाई मानते हैं, हाई इन द सेंस मच ग्रेटर देन 1, अगर थोड़ी अच्छी वैल्यू है तो आप एक एक्सप्रेशन निकाल सकते हैं जो भी करेक्ट और ट्रू तो नहीं होगा, एग्जैक्ट वो तो नहीं होगा जो ये चीज है इंटीग्रेशन, बट जो वैल्यू देगा वो काफी हद तक इसके नजदीक होगी. तो इसे बोलते हैं वी कैन ऑब्टेन एन अप्रोक्सीमेट एक्सप्रेशन फॉर द प्रोबेबिलिटी ऑफ एरर. ओके, in this scenario, let us say large m. First of all, okay, let us obtain an approximation for theta less than equal to pi by 2. We can approximate. सबसे पहले तो PDF की approximation लिखते हैं कि ये PDF approximate की जा सकती है twice of e upon pi m naught cos theta into e raised to power minus of twice of e by m naught sine square theta. So one important comment here that I am not discussing this approximation. So few of the things we generally do it in our postgraduate courses. Okay, so I am not doing this two things here. One is I can derive this as well, and secondly I can then, assuming that theta is between minus pi by 2 to pi by 2, I can obtain this approximation as well. But for our understanding, for the final result which we need to know, this is not required. So I am not doing that. But this can be easily done. Okay, so if I use this approximate expression for this PDF, then I can obtain the approximate expression for P of m as this, which is 1 minus root of twice of e by pi n naught cos theta e raised to power minus of 2 e by n naught sine square theta d theta. Okay, now this is the expression which you get with by change of variable. This can be approximately written as 2 upon root of 2 pi integration root of and not sine of pi by n e raised to power d. Okay, and this is nothing but twice of q of sine of pi by. Okay, so this is the expression for the probability of error. Okay, this you will find in terms of error function in Haken's textbook. Okay, let us see this where the author has given this. Yes, this is what you will find. So you will find this expression in terms of the error function, and we have obtained it in terms of the q function. Okay, so you can just do you can say some, I think this transformation of error function to q function we have already discussed, so you can take it from earlier notes or from lectures done earlier. Okay, notes which have been uploaded earlier. Now one thing, that if P of m is same as, so what is the average probability of symbol error? This is simply summation probability of error if you transmit E. What is this? This is probability of error when you transmit MI. Okay. What we have said is that probability of error for MI is same for all I, because of this circular symmetry, same for all I, which is equal to P of M, which is same for all I due to circular symmetry. Okay. So this means that this is suppose P of MA, this is the average probability of error. So this means this is equal to, let us say P of M summation I is equal to 1 to capital M, P of I, and this is nothing but 1, which is equal to P of M. So you can say that the average probability of simple error is also this. So let us see what Haken has written. And this is the chapter is the average probability of simple error for coherent MPS case. Okay. So now they have written that the approximation becomes extremely tight for fixed M as E by N naught is increased. Okay. So this you can basically, I don't think that in laboratory we had given this exercise, or if at all you have just compared the performance there, if at all you have drawn it, then you must know it. But I don't think that I gave any exercise on MPSK. Mostly the exercises were on QPSK and BPSK. QAM there might have been one exercise, I don't remember, but QAM we have not covered in the lectures because we didn't find enough time. Okay. So now the last topic which is remaining is that of bandwidth efficiency, okay, or power spectra. Basically, power spectra is what is, I would say, the last topic which is remaining. So this is the power spectra of BPSK, QPSK, and MPS. So I will record another video and will upload it. Okay.